Okay, let's get started. Thank you, everybody, for coming to our final Center for Robotics and Biosystems seminar of the 2023-24 school year. It's my pleasure to welcome Dr. Terry Fong, a long time ago classmate at Carnegie Mellon when we were doing our PhDs together in robotics. Terry got his undergraduate and master's degrees at MIT before going to Carnegie Mellon and get his PhD there in robotics. So Terry is the chief roboticist at the NASA Ames Research Center and the deputy rover manager for VIPER that he's going to be telling us about today. Terry previously led the development of the Astro B free-flying robot, which was deployed to the International Space Station in 2019. He's published more than 150 papers in space and field robotics, human-robot interaction, virtual reality user interfaces, and planetary mapping. So please join me in welcoming Terry.
Thanks, Kevin. Good afternoon, everybody. I'm amazed to see you all here because, number one, I've been informed that this is graduation weekend, so maybe you're not graduating. Number two, this is lunch hour, so maybe you're not eating lunch. But in any case, glad to see you all. I have not been on this campus for many years, even though I grew up in suburban Chicago and my brother went to school here. So that's just on me, but it's great to be here and it's great to actually to see you all. So as Kevin said, I'm going to tell you about VIPER, which is NASA's first lunar robotic mission. I've been working on VIPER for the past 5 years, but before that, there was a predecessor to VIPER called Resource Prospector, which was in development for another 7 years. So I've basically been working on this for 12 years, which is an enormous period of time to work on anything. VIPER is a mission that's intended to go to the moon. It will launch hopefully within the next year, although the launch date is beyond my control because it's actually being carried by a commercial launch and landing system here. But I want to start off by just telling you a little bit about the moon. In case you're not all here focused on lunar research, which after hearing some demos this morning and talking to Kevin, I assume the answer is probably not unless you do it as a hobby. 2 decades ago, the moon was considered a very different place than how we understand it today. The studies of past samples that were returned by the Apollo missions, as well as what we could see from Earth, have basically concluded, oh, the moon is really boring. It's all relatively constant. It's just dirt, and it's very bone dry. Nothing interesting to look at. But over the past 20 years, there's actually been this wonderful revolution in our understanding about what the moon is and what it has. And in particular, one very interesting thing is that we now believe, and we have some evidence to say that there's actually a lot of water, at least in terms of small amounts of subsurface hydrogen in various forms, which could be water ice, but could also be other forms of hydrogen in the lunar subsurface. And this has been due to a number of missions that have basically done remote sensing of the moon. So we've had, for example, the Lunar Reconnaissance Orbiter, as well as other orbiting missions to get higher resolution information and to use different instruments, as well as a mission that NASA Ames led several years ago called LCROSS, which was an impactor mission. We basically engaged with the moon in a very controlled manner, basically slammed a large piece of metal into the moon, and there was a big amount of release of materials from the subsurface in the Cabeus crater that was observed by lots of different telescopes in orbit and from the Earth. And based on that, and looking at analysis of what we found from the ejecta plume, we now understand that there is water on the moon to be had. And that is actually a radically interesting thing, because what this means is that the moon is not just our nearest planetary body, but it's a place that we might be able to use as a place to get resources from. Obviously, humans, if we need to actually live and survive, we care about things like water, we care about things like oxygen. If you have subsurface water ice, you can obviously get both of those things. If we want to go explore beyond the Earth-Moon system, you obviously need fuel as well. And so it may turn out that the moon is the greatest resource we have in the inner solar system to support human exploration beyond the Earth.
The future of human space exploration is being driven by what we can discover and accomplish on the moon. And with NASA's confirmation of ice existing at the lunar South Pole, the critical task of finding and mapping where water exists, what form it is in, and where it came from can now begin. Leading us on that journey will be NASA's first mobile robotic mission on the moon, known as VIPER, the Volatiles Investigating Polar Exploration Rover, It will be delivered to the Nobile region of the South Pole as part of NASA's Commercial Lunar Payload Services Initiative. This region sits just outside the western rim of Nobile crater and covers an area of 36 square miles. As the first ever resource mapping mission on the surface of another celestial body, VIPER will roam the surface equipped with 3 science instruments and a drill to detect and analyze various lunar soil environments at a range of depths and temperatures. The rover will venture into permanently shadowed craters, some of the coldest spots in the solar system, where ice reserves have been preserved for billions of years. NASA had 4 critical parameters when choosing a landing site for VIPER: available sunlight, Earth visibility for communications from the Moon to the Earth, data showing the potential presence of water and other resources, and terrain that is well suited for VIPER to navigate. The area to the west of Nobile crater met these conditions. Once on the surface, VIPER's mission will last 100 days and cover between 10 to 15 miles. And while a baseline traverse route through the Nobile region has been identified for the rover, the scientific discoveries VIPER makes along the way will actually influence where the mission team sends it next, so its planned route will most likely change. During its travels, VIPER will visit at least 6 locations where data suggests ice could be found. By helping determine the locations of where water and other resources exist, VIPER's findings will help pave the way for future landing sites under NASA's Artemis program. The prospects of achieving a long-term human presence on our moon never looked so bright.
So in a nutshell, that's what VIPER is. It's a mission to a region near the lunar South Pole. It's actually expected to operate for about 100 Earth days, driving up to about 20-kilometer total drive distance. The primary objectives of VIPER are to characterize the distribution, that's both the lateral and vertical distribution of subsurface volatiles, to provide this information to help evaluate the potential for lunar in-situ resource utilization. And part of that is this is ground truth that will allow us to generate larger scale regional maps of resources, in particular subsurface volatiles. But it's a very challenging mission. It's going to the moon in a highly dynamic environment in terms of especially lighting. We're heading for a site that is about 84 degrees south, and therefore the illumination angle from the sun is really low. It's perhaps like 5 to 8 degrees above the horizon. That leads to long cast shadows, very quickly moving shadows. Shadows move, perhaps 2 centimeters per second, which doesn't seem fast in terms of human speeds, but in terms of what rovers see, it's really fast. And it's a mission that's intended to be real time because we can operate it interactively from the ground. Unlike past missions to Mars, we have just a few seconds of round trip communications delay and are able to basically look at these science instruments on the rover in real time and make real time decisions and real time plans. VIPER fits into this sort of map of how do we deal with lunar resources, and that we've had a lot of orbital observations, past missions like Lunar Prospector, LRO, the LCROSS mission, and we'd like to get to a point where we could actually take advantage of these resources, and in particular, perhaps through commercialization of basically mining and production of these resources. We're looking at a future that's not just a government-centered way of thinking about how do you operate on the moon and beyond. And so VIPER really bridges the gap between the orbital missions to getting to a place where we can ground truth and then use that to build the future directions for lunar resources. Now, where is water ice at the poles? I will be the first to admit I am not a lunar scientist. I just happen to work with them. And we've spent a lot of time talking about areas that have the right conditions to, number one, allow the capture of volatiles, which often come from things like the collision of comets or meteors or anything else that could deposit materials on the moon, and areas that could preserve those materials over long periods of time. So VIPER has basically identified 4 different regions that we're going to try to explore and acquire measurements of. Areas that are considered to be dry, that is, it's too warm to have long-term ice stability. Areas that are deep, where the ice is stable between 50 or 100 centimeters from the surface. Shallow, where it's stable within the near subsurface. And there are even areas, especially in permanently shadowed areas. These are places which never see sunlight and are about 40 to 50 Kelvin in surface temperature, so a little bit cold, to be able to sustain ice permanently. And in particular, we can, through a variety of modeling, through the use of high-resolution 3D terrain models and measurements we've had from past orbiters, identify places that are permanently shadowed, and especially areas that seem to have high likelihood of containing volatiles. VIPER, as the video said, is intended to go visit several of these regions. They're very challenging from a robotics point of view because they're very cold, they're very dark. Some of these are very sloped. And another feature is we don't really understand the surface composition. There are some theories about these permanently shadowed areas that because they're very cold and dark, they haven't seen the temperature cycling that would tend to lead to compaction, they could be viewed as fluffy. That's the scientific term that our scientists tell us. And as engineers, it's like, well, what does fluffy mean? It's, well, it's fluffy. But that actually means that it's very difficult to think about how do you design a robotic locomotion system to deal with that. So this is the VIPER rover. It's about the size of a golf cart. It's 2.5 meters tall, 1.5 and 1.5 meters in terms of footprints. After it finds the right codec for this video here, it has solar arrays on 3 sides, and so it's an all-electric. It's a green robot with a primary battery here for power storage. It has 2 communication antennas, a direct-to-earth high gain antenna, and a wide field of view low gain antenna. It has 8 cameras. There's 2 on the mast, 2 on the rear, and then there are 4, basically 1 per wheel. It has a star tracker that is used for attitude estimation, as well as an inertial measurement unit inside. It is equipped with actually 4 science instruments, 3 spectrometers, and a 1 meter rotary percussive drill that comes out of the bottom of the vehicle here. It's a very interesting system engineering optimization problem. How do you design a robot that has to be able to survive in the lunar environment, which is actually much more difficult than the Mars environment for many reasons? It has to do with the surface environment in terms of like the soil, the lunar regolith. The soil is very, very sharp. It's also a big challenge in terms of like temperature ranges that we see here, having to go from operating in permanently shadowed areas where the ground temperature could be 50 to 60 Kelvin to areas which might be over 150 degrees higher when you're in sun. And so making a system that can be able to withstand both really hot and really cold is a real challenge from an engineering point of view. I'm actually very pleased to say that 2 days ago, we finished the assembly of the flight rover. So on the right there is the 100% complete VIPER rover that's actually at a clean room at NASA Johnson. I did mention earlier that the VIPER is a NASA mission, but it's being led by NASA Ames, where I work in California, with a lot of help at NASA Johnson in Houston, Texas, as well as instruments that come from NASA Ames and NASA Kennedy, which is in Florida, plus the drill itself that comes from Honeybee Robotics, which is in Pasadena or Altadena, California. And so what you see here is the fully assembled flight rover. We just finished basically building it, which means it's not ready to fly. It just means it's ready to go into testing. So for the next 6 months, there's an extensive environmental chamber test campaign where we subject it to hopefully conditions that it will experience on its mission, and hopefully it will actually survive that in good shape. And then we'll get ready to launch it to the actual moon. In comparison here, you can actually see these on the top row here are past Mars rovers, starting with Sojourner back in 1996, all the way to the Mars 2020 rover, which I think most of you probably know as Perseverance. In comparison to the bottom row here, these are things that have been on the moon. Lunar back in the early 70s, the Lunar roving vehicle, which was the Apollo Jeep, if you want to think of it that way, and VIPER itself here. So as I said, it's golf cart size. It is actually a rover which moves far faster than any of the previous Mars rovers in terms of mechanical speed over ground. We typically drive at about 20 centimeters per second, which for a planetary rover is very fast, incredibly slow for any of us, and especially compared to like terrestrial robots. But for planetary rovers, going in a really challenging environment, very uncertain, unknown conditions, it's actually quite fast. So VIPER is for NASA a new kind of planetary rover. As I said, we deal with a dynamic environment on the moon in terms of illumination in particular. We have a very strong emphasis on a high operational cadence because it's interactive with the ground. It's the very first time we're going to try to operate it from a science point of view interactively. That is, the operations team has a scientist who's sitting in mission operations and sitting actually alongside the rover driver and working in the role that's called RT-Sci, real-time science here. It's also a rover mission that, at least at the start, was meant to be much cheaper than Mars rovers. Unfortunately, you do the math, we started 5 years ago. There was something that happened across the globe, kind of really blew up the cost. But originally, it was meant to be a much cheaper system. It is as I said, interactive with the ground, both in terms of rover operations and the science team. We are operating in a kind of hybrid of the way that we operate Mars rovers and the way we deal with the space station. That is, we basically think about command cycles. So we generate commands for the rover. We make sure those commands are the right ones we want to send. We send it to the rover and it executes that. We wait for the data to come down and we replan and then do another cycle of commanding. So we're not doing real-time sort of joysticking rate control. It's very much command cycle, which is the way we operate the rovers on Mars. However, that command cycle is about 4.5 minutes per cycle versus Mars, which could be a day long and certainly as many hours long for most of the time. So it's very continuous, it's very short. It's very much similar to the way that you operate robots on the space station and interact with crew on the space station. And in terms of the avionics on board, we have this interesting challenge of how do you make a more capable rover that has to operate within a very difficult radiation environment with spaceflight computing that is, as powerful as like a 1997 PowerMac G3. That's our main processor. It's a RAD 750. It's a radiation hard processor. Nobody in this room would ever want to use that for anything. I'm sure of that. We do have a more modern, RAD tolerant power PC that's 1 gigahertz. So hey, we're at 2010 iPhone 4. So I mean. These are still, still I think fairly good computing for space missions. But just to give you an idea, I mean, this is one of those big challenges. People come to NASA and they think, oh, hey, I did all this great work in my undergrad work. All I need is, an 8-core high performance processor. I'm like, well, no, you can have a power PC. I will say, however, we are trying to do things a bit differently. So, for example, we are using ROS2. As part of this, not on board, but as part of our ground software. So for VIPER, we decided because it's an interactive mission, because it's at the moon, we can do something radical, which if you take the software, we can basically split it apart. So some portion of the code base, which would normally be inside planetary rover, it was going to Mars, actually runs on Earth. So we run that on Linux machines that are sitting here. We connect basically, the flight software on board the rover to the ground software via data communications. And as a result, we can use ROS2 on the ground. So we're very excited about that. In terms of the design itself, I know that a lot of you come from mechanical engineering. So I'll have a couple of charts in here that talk about the overall mechatronic design here. It looks very different than Mars rovers. It only has 4 wheels. It doesn't have what you've seen before from NASA, which is a 6-wheel rocker bogie configuration. And part of that is driven by the fact that we are very uncertain about the environment that we're going to encounter on the moon. And so we chose to create a system where we have a 4-wheel system, but a controllable active, I hesitate to use the word active. Active is all relative. I would say controllable adjustable suspension system. So each of the wheel axes, each of the wheel modules here has independently controlled propulsion, steering, and suspension control. And that allows us to do all kinds of things with this vehicle that we cannot do with a 6-wheel rocker bogie configuration. So for example, we can independently control each of the different wheel modules. So we can do things not just like driving, but we can actually wheel walk. We can change the track width between the vehicles because we have the ability to control the suspension. And that's been very interesting for us. It has 50 centimeter wheels. We've targeted to be able to drive over about 20 centimeter scale obstacles, whether those are positive obstacles like rocks or negative obstacles like small craters. And it's been a very interesting development in terms of just the locomotion capabilities because it's so radically different than past rovers. One of the challenges we have, of course, is how do you build and test something like this on Earth that's destined for the moon? And the best way of doing that, of course, is to try to make it as kinetically and as dynamically similar as possible because you'd like to test as you fly, which is sort of like the big thing that NASA really emphasizes. Because the moon has 1/6 of Earth gravity, however, the best way we can do that is if we can't just do a gravity offset is we have to take the system and reduce its mass to 1/6 of the mass that it will be launched to the moon. And so this is our mass equivalent prototype. It's 1/6. It's very trimmed down. You don't see things like solar arrays. You don't actually see even like power electronics, a lot of the stuff is being moved off board. But it allows us to focus just in terms of mobility testing on the key elements, that is the drive, the steering, the suspension, and to some respects, the integrated navigation with that. This will work. Yeah, okay, so this is actually, I think this was our second prototype. It's not exactly the same as the flight design here, but just to give you an idea of the ability to be able to manipulate the chassis posture, to change the track width, to do all kinds of calisthenics. You know, if you want to have the exercise robot, this is the perfect platform for that. Done a lot of testing. Sound of that. Tell you that we have been trying to do this testing of robots and been driving many kilometers, testing the wheels and doing all the input testing. It's actually formed by Federal Innovations, which is a the wheel design. So doing a lot of extensive testing like that's important for a rover that's going to a very difficult environment. We also have this interesting facility at NASA Glenn in Cleveland called the Slope Lab. You can probably guess why it's called Slope Lab. It's a place where we have the ability to test out locomotion and thermomechanics in a very high fidelity and controlled manner. So we have a variety of different soils. In this case here, this is a soil called GRC1. It's a lunar simulant that's considered to be fairly high fidelity for thermomechanics for the moon. And we have done a lot of controlled testing here of VIPER, including putting it in places where it's very deeply entrapped, testing slip overall. And you can see that's how it's slip. Also done a lot of testing beyond this sort of solid overall. Driving over those kinds of environments. We've also tried to put it into places that are very difficult to get out of. So in this case here, we have a crater that's the same scale as the rover, really challenging for pretty much any sort of vehicle. And use that to develop a number of alternate mobility modes. Now, normally when VIPER operates, it drives with the four wheels. It normally does explicit steering, but it also allows it to basically crab in most directions. However, in case we end up getting embedded or even entrapped in especially very unconsolidated material, we've been developing these alternate gates here, which use combinations of drive, steer, and suspension control. And we can do all kinds of things from inchworming to this is maybe like a butterfly stroke. This is maybe like a snake, and that's called a groundhog only because it's popping its head up to see what's going on. And of course, we can do all kinds of different combinations of these different modes. It's something that we've never done before at NASA in terms of making vehicles traverse terrain in unusual ways. Now, of course, we're not going to use these routinely because the drivetrain wasn't designed to operate continuously in this kind of mode. But if you have a really bad day, if you get stuck, it's nice to be able to have this in your pocket as a way to perhaps get unstuck. We've done a lot of testing over the past couple of years also in terms of egress. We are meant to be carried to the moon by a commercial company. It's Robotics, which is a spinoff from Carnegie Mellon on their Griffin 1 lander. And then after it lands on the moon, ramps will deploy and VIPER will have to drive down the ramps. So we've done a lot of testing. From an engineering point of view, you would think that maybe the ramp design could be better, but that's Robotics design. It's not our design. So we have to then still be able to egress no matter what happens with the ramp. So we worry about, what is the height differential between the two rampways? Is there splay either toe out or toe in? Is there twist with the ramps? And because we have a controllable suspension system, we can compensate for a pretty wide variety of things. But we've had to do a lot of testing to convince ourselves that we know how to do that. We've also had, actually, I wasn't sure, should I take questions in the middle or?
We can do quick clarification questions and save the big ones.
Okay, so quick question.
You mentioned splay, like how much ability to have the wheels go in and out?
It's, we can probably deal with up to about 15 centimeters or so. It's not a ton, but it does allow us this. And, obviously we don't want to drive outside of the rampways and then, fall off and then get stuck that way. It's something we've been doing a lot of work. And right now, the past few weeks, we've been doing some outdoor testing at nighttime so we can do simulated lighting conditions as well. We have a sun simulator, really bright light at nighttime. Makes it look like NASA's doing very strange things for aliens. But In any case, we also do work in making sure that we can do something which seems very challenging, but has actually worked out pretty well, which is basically maintaining stable pointing while under motion and driving over rough terrain. VIPER operates with a comm system that is line of sight to the Earth, either a wide angle, sort of low gain antenna, so it's very low bandwidth, or a very directed, narrow beam angle, high gain antenna. But that means you have to point it at Earth all the time in order to maintain communications. And so what we've done here is a bunch of nighttime testing where we're driving over rough terrain and verifying that we can point, in this case, at the moon, because we can point at the moon, then presumably we can then point at the Earth when we're on the moon. We've also done a fair amount of camera light testing, both outdoors and indoors. This is at an outdoor test area at NASA Ames. And these look like really incredibly hazardous craters here, but these are actually very shallow craters. If you saw it in the daytime, you wouldn't even notice them. But because we're talking about the lunar poles, where I said we have these very low angle sun orientation, we end up with these really long cast shadows. So even small features like this is probably like, I don't know, a 3 centimeter bump here casts a shadow, makes it look like a big obstacle. It's a very challenging thing, whether you're talking about human perception or automated perception here. Just the lighting environment, is really challenging. Of course, if you're a computer vision person, you look at this like, oh, this is great. I can use the shadows to reconstruct the environment. And yeah, that's fine, but we just want to avoid the obstacles. So there's a little bit of a tension there. I mentioned we do indoor testing as well. One of the other facilities we have at NASA Ames is a 4 meter by 19 meter sandbox that has 19 tons of LHS-1, which is a lunar regolith simulant that's high fidelity in appearance. So we can use this test bed for doing camera testing, and VIPER is equipped with its own lights. So it's the first rover that's going to have basically headlights. And we can use that, the combination of the lights and the cameras to image, even if we're going into permanently shadowed areas. So this is a test bed, and this is the flyover if you're very low and what it looks like. We actually have captured a number of different data sets, which we've released. If you're interested in perception for the moon, especially from the point of view of a rover that's going to traverse, you can easily find some of the data sets that we've released out and take a look at how you could use those in your own work. Now, let me switch topics here and talk a bit about mission planning. Now, VIPER is a short duration mission. 100 days is not very long. And in fact, 100 days is the total mission duration, but the actual number of operational days is probably much lower, perhaps 40 or 50 of those days. And so having good plans and efficient and effective plans are really important in order to be successful in acquiring the science measurements here. So we've spent a fair amount of time over the past 5 years developing methods for doing activity, resource, and traverse planning. That's both at the strategic and tactical level. And we're trying to do this to come up with ways of achieving full science mission success under significant uncertainty. So a few of the constraints we have to worry about from a planning point of view are, the distribution, the state of lunar polar volatiles. What does that look like to the instruments in terms of the measurements? It's a solar powered rover with limited battery. That means limited time it can be in shadow. Only 100 Earth day total mission. We have to have line of sight data communication to Earth. We're going to drive up to 20 kilometers, but we need to negotiate slopes. We have a target design of 15 degrees and slopes and 20 centimeter step obstacles. You can only drive 10 centimeters per second while using certain instruments, and these moving shadows move up to like 2 centimeters per second. So those are a few of the, several dozen constraints that go into planning. Any of you are planning people, wonderful research problem, horrible engineering problem. We have made a lot of progress though in terms of creating high resolution digital terrain models. We end up with data that starts off from an orbiter. The Lunar Reconnaissance Orbiter provides stereo cameras as well as laser altimetry of the moon. We take that and we apply methods to get high resolution. That's basically like 1 meter per pixel surface resolution models. And we do a lot of work in terms of comm, illumination, stability modeling. That leads into high level strategic planning of traverses and then detailed tactical activity planning. And what we end up with are things like this. So this is a traverse plan. This is obviously like last year here. What you can see here is the arrow is pointing at where the rover is, and it's a game of kind of chicken. You're trying to run away from the shadows and follow the sunlight, and it's very dynamic, which means that, if you get stuck in one location, the question is how robust is the trajectory? Can you still make it to another area if you wait? How long can you wait? It's a very fascinating, like I said, planning problem. And it's something that we've not had to do before for Mars rovers, because we typically operate during long, extended, well-lit summer seasons in equatorial regions. But for the moon, that is not the case. It's been very, very interesting, challenging, and horrifying at the same time. We've also spent quite a bit of time developing simulation. It's really needed for, I think, two main purposes. One is from an engineering point of view, because the moon is such a different environment than we see here on Earth, it's hard to recreate in terms of facilities. So we've been trying to rely heavily on simulation, both appearance and physics modeling for testing and engineering purposes, as well as for mission operations development. How do you operate the robot? How do you train the operations team to do that? And so we've, focused on trying to take, at the base, we started out with just the sort of vanilla gazebo. We've added a lot of things to that in terms of high dynamic range rendering, real-time shadowing, high resolution lunar terrains, all these things that are really important from a mission operations training point of view, like rover wheel tracks, slip modeling, and for engineering points of view, making the camera models very, very high fidelity. So not just the things that you find an off-the-shelf gazebo, but things that are necessary for its use for mission simulation. Let me skip over this slide here. Some of the things that we've done have to do with high quality lighting. We've been trying to model the lunar surface appearance in terms of things like there's an effect called the opposition effect, which is basically if you're looking at the lunar regolith straight down sun, so the sun's behind me and looking straight forward, it's artificially brighter in the center, where it's aligned with the sun vector, and that's because of the grains of soil end up giving sort of coherent backscatter effect. And so it makes it really interesting from how it changes the visual texture of the moon, but you have to be able to model that, something you don't see here on Earth. We've also worried about Earth shine, this idea that reflected light off the Earth actually illuminates the moon, especially in permanently shadowed areas to some extent. And of course, have to model the effects of rover lighting. Camera models are really challenging. There's a lot that we rely upon for us to be able to do development of things like navigation that relies on cameras. So we've added a lot more detailed models than you would ever find in any sort of off-the-shelf standard sort of simulation software. Worried about like fixed pattern noise and reading noise, pixel defects, and things like that. And very interesting in terms of the simulation. And so we can do things like this. This is an actual picture from that lunar lab inside of the simulated terrain here. So you can see rocks and craters here. And that is a simulated version of that starts off with the 3D mesh here, but then goes through and uses all the things we just talked about in terms of illumination and camera models. We've also developed these high resolution synthetic terrains that start off with real lunar data, but then augment that to get to even higher resolution data that we can use from an engineering point of view. So orbital data, which might be 50 centimeters per pixel or 1 centimeter per pixel, is great if you have an enormous monster truck. It's not so good if you're trying to worry about wheels that can only deal with 20 centimeter obstacles. And so we generate high resolution maps here that have a basis in orbital data, but then we want them to be high resolution and still be somehow scientifically plausible. So the way we do that is we've had a lot of work over the past, I guess, 3 decades in terms of lunar science, and we end up having these very detailed size frequency distribution models of things like craters, as well as lunar rock models. We can take that and we can take, for example, base data. So this is like a digital elevation model from actual orbital data, and then we can scale this up in some way, and we actually use a fractal method to increase the resolution. We can add in craters here, and we can, based on also distributions of the age of craters, make the older ones more degraded, more weathered to some extent. We can then add in small synthetic craters. We can add in synthetic rocks. And at the end of the time, you end up with things like this. So this is a real-time rendering. This is, as I said, gazebo at its base, although it looks nothing like gazebo that most of you would probably work with. And here, this was back in 2020, showing a prototype rover where we have real-time shadows. There are rover tracks going on. And in terms of appearance to the moon, based on analysis and discussions with our lunar scientists, we believe was very high fidelity here. Let me skip over in the interest of time here, showing you this is where we are currently here. So this is including high resolution synthetic terrain and the actual higher quality model of the VIPER rover. This is the system that we're currently using, and that's both for engineering purposes. Right now, it's basically requirements verification in terms of our navigation system, and right now also for mission operations training. Hard to see on here, it's a little bit better over there on that monitor here. This will take me to the last part of this talk here. I was trying to leave some time to have some discussions, since I think you probably have some interesting questions here. The last bit that we have started focusing on over, I guess maybe the past 9 to 12 months, has been mission operations. This is a different kind of mission because it's interactive with the ground. It's something that we haven't done before. So early on, we recognized the need for developing a very specific way of operating with the rover and then training the operations team here. And so this is one of the control rooms at NASA Ames here. We have a front row here with a team that's considered the drive team. So we have a real-time scientist here. This is the rover driver, the rover co-driver, and the navigator. In the back row, that's where the flight director, the systems person, command operators sit. And this is connected to a number of other mission operations room involving the instruments as well as rover systems support. And we use a variety of interfaces, interactive 3D interfaces, 2D map interfaces, and lots of low-level displays for thinking about how do you operate the rover. The mission itself, as I said, is going to operate over 100 days. The video at the beginning indicated it was near Nobile crater. That area has since been named. It's actually Mont Mouton. It's a large area on the western side of the Nobile A crater area. And the way we operate is after landing, we will drive to a variety of science stations. And within the science stations, there's a lot of detailed plant activity. But then between science stations, it's basically trying to get from point A to point B as rapidly as possible. We operate the entire rover in an interactive manner with this command cycle, like I said, every about 4.5 minutes. And each one of those command cycles is meant to have the rover advance on the order of 5 to 10 meters at a time. So it's a kind of continuous stop and go where you're basically planning out how to move the rover from point A to point B over and over again. It's just if you're in science stations, that's overlaid with lots of specific activities about where do you need to take measurements, how do you take measurements. Measurements could be with the 3 spectrometers, it could be with the cameras as well, and all done in an interactive fashion where you have an a priori plan, but you're modifying that plan based on what the rover encounters, based on the data the science instruments return. And I'm just going to show you here something I spent a lot of time looking at because I will admit that I actually have a second job. I'm not just the rover deputy manager. I'm actually the co-lead rover driver for VIPER. So that's the reason why I went to NASA originally many years ago. I'm looking forward to actually being able to operate this rover on the moon. And so one of the things we use is this interactive 3D tool where we have a variety of displays, including camera imagery. We have a 3D view here that shows the rover, and overlaid in the center here is this multicolored hazard map that is based on the rover's stir information that we process, and then we assess hazards in terms of slopes and step obstacles, positive and negative. We overlay that with 3D information about the terrain that may be a priori data from high resolution orbital sensing. We overlay other information such as traverse path, comm corridors, the estimated path of the vehicle in terms of its estimated location. And we operate it by commanding waypoints. So you can see here, on this side, this is the operator interface, and then over there is the simulator. You basically set out a waypoint. In this case, it looks like it's about 9 meters away from the rover. The execute drive, this is actually driving in an area that's actually fairly benign. It's colored green and yellowish. And then at some point later, those commands are sent over in a simulated time delay and the rover starts driving. So if you were on the moon, this is what you would see. Of course, the operator doesn't see that. The operator only gets images that are taken by the cameras when you command those images. And everything in between, sort of stopping and images you don't know on the ground, which is one of the big challenges we have of operating rovers like this. It'd be great to be on the moon and just like control it in real time. But instead you have this sort of like limited view of the world, and trying to build up good situational awareness is always a challenge from a rover operations point of view. With that, I think I'll wrap up here. Happy to take any questions about VIPER, but one final comment I just want to let you know, since I assume there are a number of students here. Pretty sure that you're not all faculty. Both undergrad and grad. One of the things that's very important at NASA is engaging students in the work that we do. And one of the most interesting programs, which I think is the best program that NASA has, is a fellowship program called the NSTGRO. I apologize because everything in NASA is acronym based. NSTGRO stands for the NASA Space Technology Graduate Research Opportunities, or as those of inside like to refer to it as the InstaGrow program, just kind of water kind of thing. But it's a graduate fellowship program that's open to seniors who are heading to grad school or anybody who's in a graduate program for any duration. You could be a master's student, you could be a third-year PhD student, and you can apply for this fellowship. The fellowship actually provides support for you to do research, not just here at Northwestern, but you actually are assigned to a NASA research collaborator whose time is covered 5% of their time. So they are motivated to actually spend time in research with you. So it's not just like talking once a year, you actually talk continuously. And it provides a little faculty support. So faculty are then highly motivated to talk with you and the NASA researcher about joint research. So it's a great program. Been going on for, I think, 14 years now. The next call for proposals comes out just after Labor Day. So if you're interested in things like I've talked about today, or learning more about NASA, I highly encourage you to check out InstaGrow. But with that, I'll stop and I'm happy to take any questions about VIPER. Yes.
I was very interested in the new wheel mobility capabilities, like you have those interesting gates. Something that immediately strikes me as challenging about that problem is that the terrain is being like remodeled in real time. So let's say that you do find yourself in a position where the rover is just like stuck and you need to do one of these gates. Is there any sort of closing the loop around that process, or is it like an open loop gate, like let's do the best we can and see what works?
So all the gates that we have are parameterized in terms of like number of cycles and like, ranges. You can do the butterfly stroke out to a certain range, and you can obviously try to target that for specific particular situations. But again, it is a very difficult thing because, as you say, you might be remodeling the terrain as you're driving. And so it is for us viewed as basically an anomaly response. And the question, of course, is going to be also, once you start getting unstuck, when you determine that, hey, I'm actually unstuck, I can resume normal driving. We don't have a really precise answer right now. That's part of what we've been doing for additional testing. And I had a meeting just a couple of days ago just talking about the overall process. But what you said is really important. You basically rely on these sort of alternative gates because you're in an anomalous situation. By definition, it makes it hard for you to understand exactly how much you should try to get out, or how you might even combine different gates together, because we can run multiple gates in sequence, or even try to combine them in some way. We probably wouldn't combine them real time during flight. We'll probably use ones we've tested, but even just trying to say, well, we did 5 cycles, 10 cycles, 100 cycles, it's hard to say. Yes. Yes.
So not a technical question, but how did this project end up at Ames instead of JPL? Because it seems very much to fit their skill set.
So NASA as a whole runs missions from most of the centers, not all the centers, most of the center. NASA Ames for a long time is considered to be the lunar center. We have run several missions, Lunar Prospector, LCROSS, the LADEE one, which was basically an orbiter mission. Those were all led by NASA Ames. And so when it came to the development of VIPER, which is a lunar surface mission, there was some discussion, but it was still pretty evident based on past history, and especially because the lead scientist for this was the lead scientist on the LCROSS impactor mission, but that's how it ended up at NASA Ames. Yes.
I know you mostly talked about the rover itself, but I was curious if you could talk about the data collect or the actual sample collection. How much you have to worry about like cross contamination between different sites and stuff like that when you're actually, and do you dump the like, let's say you take all the measurements, do you dump the rest back on the moon?
Yeah, so I didn't have a slide that talks about the science payload on the rover. There are 3 spectrometers. There's a neutron spectrometer that's basically just detecting what happens is galactic cosmic rays basically collide with the moon, and in the subsurface, when they interact with hydrogen, there's a certain amount of returned neutrons, and we can detect with this neutron spectrometer basically the energy of those neutrons. That tells us something about the materials. A second one is a near IR spectrometer, which of course has to observe directly a particular material. Third one is a mass spec. And what happens is that we go to a number of locations where we use the drill to access subsurface materials, and as those tailings are pulled up, we're using the mass spec and the near IR spectrometer to analyze the mineralogy of those materials. Now we don't do that all the time, and so we may end up driving for many days between drill sites. And the drilling and the use of those two instruments are really the way we assess the subsurface. The neutron spectrometer, however, is used all the time. It's always on, and we're continuously mapping basically the subsurface. So it's a combination of basically the fact that we're doing continuous measurements and then occasional drill subsurface assays as the overall approach for acquiring science methods. Yes.
So you mentioned you worked on this project for 12 years. Is this the only thing you did for 12 years, or do you have several tracks and some projects make it to the finish line and other ones get scrubbed? I'm just curious what breadth and width there is in your tasks, for example.
Yeah, so me personally, no, I actually worked on a bunch of things over that period of time. We just started the resource prospector mission development about 12 years ago that actually got to sort of like preliminary design phase. At that point, NASA decided that there wasn't sufficient budget for that, and there was a change of which part of NASA was going to pay for it. And so that mission was canceled, and then a year later, VIPER was reborn to follow on from that. But in parallel, as Kevin read earlier, I've done a project called Astrobee, which resulted in these free-flying robots that are inside the International Space Station now. They're kind of boxy. If you're a Star Trek fan, they kind of look like board cubes. They're like 30 by 30 by 30 centimeters. And you can put various payloads on there. You can put manipulators or sensors or add on new computing. But they fly inside the space station. And they're actually currently the most used in-space facility on the space station. And it's the only actually open space robotics facility in space. So, we actually have variety of researchers, and we have school kids. There's actually something called Zero Robotics, which is, I don't want to call it first robotics in space, but it's kind of something like that where you basically develop code and you run it on the space station on these robots. And those systems actually launched in the end of 2018 and were activated in 2019. So, yeah, we've had some fun over the past decade. Kevin.
So I suppose you could have called this Project VIPER if you're just looking for water. I wonder what other volatiles are. Can you define that?
Yeah, so there are a number of people, a lot of people in the space community that are interested in off-world resources. And there are obviously questions about what sort of resources can you find on the moon versus other places, Mars, Europa, or other places that may be even more distant. For the moon, the primary interest has been on volatiles, and in particular, anything that has hydrogen with it. Water ice is one, methane is another. Because hydrogen is such an important element to base element. We already know that from other parts of the moon, the base sort of regolith, it's something that you can basically reduce and extract oxygen from. So we have a ready source. We know that we can get oxygen pretty much anywhere from the moon. But hydrogen is a really interesting thing, that if we can actually locate that and determine that it is actually accessible in some way. So there's always the questions of, well, hey, if it's like 2 meters deep, maybe it's just be too hard to get at. Or if it only exists in large quantity deep inside a permanently shadowed region, how do you get in and out? And you can't just leave equipment in there. It's incredibly cold and incredibly hard to just keep it warm all the time. So those are the questions that the space community is now trying to address. VIPER is the first mission, even though it's a science mission, in some sense, it's a bridge between science and the resource community. And we've had a lot of development, especially in terms of the science measurement plan that's been informed by the way we prospect for resources here on Earth. We work closely with, for example, like USGS. We've taken a lot of inspiration from like the oil and gas communities of how they basically prospect for oil and gas here.
So one other question for you. The wheels, going back to Tom's question earlier, can you tell me how many degrees of freedom each wheel can be moved in addition to its spinning forward?
Yeah, so there's the spinning, so that's the drive propulsion axis. There's a second one that we use for steering. It's like plus or minus 45 degrees, I think. And then there is a suspension arm, so we can basically control the height of that wheel module. So, you know, you look at that, there's 12 degrees of freedom total in terms of the ability for just like wheel-based locomotion. It is interesting too, the fact that we have been trying to use those for not just driving, but for other capabilities too, like trying to keep the chassis as level as possible as you're going over terrain helps out in terms of making it easier to point at the earth. You're not going to worry about the whole chassis pitching, but if you can basically have the chassis basically float as you're going up and down slopes to some extent. Obviously, you can't, if you go up a really steep slope, you can't just level because you're running into the limit of the actuator. But for 15-degree slopes, there are orientations of the vehicle where you can still maintain the chassis level or relatively level up until the full extension of the suspension arm. Yes.
Can you talk a little bit about your data pipeline? Like you mentioned, there are some instruments that were running continuously. Do you have to rely on constant contact with your high gain antenna? And like, how does that bandwidth work for processing data and sending it all back?
Yeah, all space missions have this fundamental problem of data, basically transmission management. We obviously have onboard storage, data storage. We can store data from not just the science instruments, but the engineering sensors as well. You know, we can, for example, you know, sample like the inertial measurement unit at 100 hertz, but we're not going to transmit that data to Earth. We will basically store it and then we'll forward it at some point in time. And that's based on, you know, decisions about what's the most important data at any given moment in time. So for example, if we're driving between science stations, you know, the science payload, I mean, data is viewed as less essential because we're trying to make the rapid process. So during those periods of time, you know, rover operations gets the benefit of more bandwidth. But we do, you know, try to capture, you know, the most important measurement data and downlink that as rapidly as possible, just in case the rover dies, because we want to get the measurements first. And then on the ground side, every mission has what's called the ground data system, which is basically the system that we use for managing the data in terms of where is it stored, how's it accessed for both real-time assessment and then long-term analysis. And then post-mission, we'll take that data and we'll release that out to something else. For example, there's a planetary data system, it's a distributed set of data archives for different kinds of missions and different science. And so VIPER's plugged into all of that. Yes.
Did I understand that you said you got a 4-minute drive command interval?
Yes.
So with communication latency of just 2 seconds, where does that 4 minutes all go?
So the 4 minutes is really constrained because in order to make decisions with ground in the loop, we need to provide a certain amount of data for the ground to make decisions. The biggest constraint on that has to do with imagery. And so because we have limited bandwidth and the data from the images that we want to basically downlink, that takes up a big chunk of the time. Once the data is on the ground, because this is not a fully autonomous rover mission, there are humans that are making decisions about, for example, is the terrain traversable, or what's the risk of going in a certain area, or trying to basically look at driving decisions as well as how they impact science measurements. And so basically, when you start the clock and you're downlinking data and then it arrives on the ground and then you're analyzing it and interpreting it and then generating a next command, or maybe you're even doing tactical motion planning, and you lay out, okay, here's the command I want to send, and then you're actually ready to send that. That all takes, you know, about 4.5 minutes when things are going really well. You know, it seems like a long time, but for planetary rover mission, it's actually incredibly fast. Yes, Brenna.
I had a question about the purpose of your simulator. So is that primarily for the pre-launch development, or is it also going to be a part of your ground software decision-making for these command cycles?
It has been envisioned, or it has been envisioned and used primarily for pre-launch development and training. Now you're right, obviously we could try to update it with information in real time and then use that during the mission, especially if you're worried about you know, anomaly resolution. Let's say you're a problem and you say, well, let's try out different things in the simulator. We haven't done that because I think that the understanding is that given that the mission is such short duration, that, you don't want to spend time saying, oh, okay, let's go spend the next 3 weeks trying to figure it out, in simulation, and we'll set up a physical test bed and we'll test that, and the mission's over before you even get up there. But it is something that is an ongoing question. There's a lot of interest, and I hate to use the words digital twin, but there's a lot of interest in that. Because digital twin, what does it mean? That's you and me probably all different definitions, but there certainly is interest of that for longer duration missions. Yes.
Earlier on, you mentioned that like one of the control methods would be like sending waypoints. I'm curious if you could talk about what like the local planning architecture looks like.
Yeah, so VIPER was designed originally to be a mission that we could develop as rapidly and as, I really hesitate to use the word cheaply, but cheap is relative. Original budget for VIPER was like $250 million overall, and that's not including launch and landing. But the intent was to try to minimize the amount of testing that you would have to do for things like autonomous capabilities. And so from a planning point of view, we basically brought everything that we would normally have on board the rover to the ground side and use that as a decision support to human operators. The operations team that I showed earlier basically is informed by that. So if you took the humans out of the loop and basically connected, the recommendations of like traverse analysis and local path planning and hooked up the rover, it would operate. But we have humans in the loop who basically review that and then use that to maybe modify the decisions a little bit and then forward that onto the spacecraft. And so in terms of the overall architecture, we rely heavily on the use of stereo vision. So we don't have any active range sensing. Even the fact that we have lights and could have tried to create a structured light system at the end, we decided, no, we'll try to have it basically as even an illumination as possible, just to simplify not just the engineering analysis, but the science analysis. So basically have stereo imaging of the terrain that comes to the ground. We do correlation, we generate local 3D meshes. We do assessment of hazards in terms of slope, step obstacles. We turn those into assessments based on the rover's capabilities for dealing with those things, and then we generate hazard scores. And those are then presented to the operators. We also do local path planning to obviously to say the recommended path over the short distance here. But again, because we're doing this in an interactive manner, we don't need to actually have a long planning horizon. We typically only look out 5 to 10 meters at a time, even if we're trying to move from point A to point B as rapidly as possible, because we know there's a lot of the world that's uncertain. So there's no real benefit other than sort of like regional trends of, okay, over the next 100 meters, we're going to go from like level to like 15 or more degree slope. So we'll start thinking about how do we have to move? Do we try to maintain cross slope driving, or is there a better way to avoid getting into very steep areas?
So,
Sorry, yes.
Why choose solar over nuclear, given your challenging shadow environment?
Yeah, 2 answers. The first is paperwork. And the second one has to do with risk assessment. So anything that uses a radioisotope, whether it's for heaters or primary power, you're automatically adding 2+ years to mission and a lot of cost. Because there's always the risk of, well, what happens on launch if something goes wrong? So we chose to be solar powered, which has all these implications in terms of operations and planning and system engineering. Yeah, I'd love to have a radioisotope generator on board.
So who has this last question?
Okay, last question. Who hasn't asked a question yet? Anybody? I wasn't sure who. All right, last question.
go ahead.
So you mentioned that you have a mass equivalent rover on it. And you also do testing at Glenn, I think, in your slope lab.
Yes.
So that's at Earth gravity and with an atmosphere. How do you go from that to on the moon at 1.6G and no atmosphere? Do you just use simulations as the glue, or is there some?
Yeah, so I mean, we try to use a mass equivalent. So we have a very slimmed down rover. So it's 1/6 the mass of the flight vehicle. It drives slowly, so it's mostly quasi-static. So we don't worry about any sort of atmospheric effects. We obviously have this issue that we can't gravity offset each grain of soil. So there is this open issue of, well, if the soil is not at lunar gravity, does that change the locomotion performance and the thermomechanics? And that, I think, is just an open, question of debate and research right now. You know, we're trying to basically, you know, take the approach which allows to do hopefully sufficient characterization of the system to understand how it will perform, you know, how much slip we're gonna see on this particular angle of slope with this particular, you know, compaction. And that's the best we can do right now. So.
All right, let's thank our speakers.